Chapter 19. Energy and Metabolic Consequences. Energy production reflects how effectively the digestive system converts incoming food into substrates that can be absorbed, transported, and oxidized within cells. The sequence from digestion to cellular metabolism is continuous. When this sequence is aligned, nutrients are delivered in forms and at rates that match metabolic demand, allowing energy production to proceed with stability. When digestion is incomplete or irregular, the availability of substrates becomes inconsistent, and the entire metabolic system is forced to adjust to fluctuations in supply. The first consequence appears in substrate availability. Proteins that are not fully reduced limit the pool of amino acids available for cellular processes. Carbohydrates that are not fully broken down reduce the supply of simple sugars that can be rapidly used for energy. Lipids that are not properly emulsified and absorbed limit the delivery of fatty acids that support sustained energy production. Each of these limitations reduces the total substrate pool available to cells, not because intake is low, but because delivery is incomplete. Timing further shapes energy availability. When digestion and absorption are coordinated, nutrients enter circulation in a pattern that supports continuous metabolic activity. Water-soluble nutrients appear quickly, while lipid-derived substrates are delivered over a longer period through transport systems such as chylomicrons. This sequence provides both immediate and sustained energy sources. When digestion is disrupted, this timing becomes irregular. Substrates may arrive in pulses or in reduced amounts, creating periods where energy supply does not match demand. Hormonal signaling responds to these changes in availability. When substrate delivery is consistent, hormonal signals align with metabolic needs, directing nutrients toward oxidation or storage in a coordinated manner. When delivery is inconsistent, signaling becomes reactive. Periods of reduced substrate availability are followed by periods of increased supply, and hormonal responses shift accordingly. This variability alters how nutrients are used, stored, and released, affecting overall metabolic stability. The physical and chemical environment within the intestine also influences energy outcomes. Increased fermentation from incomplete digestion diverts substrates into microbial metabolism, reducing the amount available for absorption. The byproducts of this process alter the luminal environment and influence motility, further affecting how nutrients are processed and absorbed. The system loses efficiency as a portion of the energy contained in food is redirected away from the host. At the cellular level, inconsistent substrate delivery affects how energy pathways operate. Cells rely on a steady supply of substrates to maintain stable production of energy. When supply fluctuates, cells adjust by altering substrate preference, shifting between available sources as conditions change. This adaptation maintains function but reduces efficiency and increases variability in output. Energy and metabolic consequences therefore arise from how well the digestive sequence delivers substrates into the system. When digestion, absorption, and transport are aligned, energy production proceeds with consistency and efficiency. When they are not, substrate availability becomes irregular, hormonal signaling shifts, and cellular metabolism adapts to a variable supply. The outcome reflects the condition of the digestive system rather than the quantity of food consumed. Incomplete nutrient extraction. Incomplete nutrient extraction occurs when the digestive system fails to convert ingested food into forms that can be absorbed and transported into the body. The quantity of food entering the system remains the same, but the fraction that becomes available to cells is reduced. This loss happens at the level of structure. Proteins that are not fully unfolded and cleaved, carbohydrates that are not reduced to simple sugars, and lipids that are not properly emulsified and broken down remain in the lumen and move forward without being captured by transport systems. The limitation begins with preparation. Gastric acid sets the structural state of proteins, exposing sites where enzymes can act. When this step is incomplete, enzymatic access is restricted and larger fragments persist. Pancreatic enzymes depend on this prior reduction to complete breakdown. When substrate structure does not match enzymatic requirements, cleavage slows, and a portion of the material remains outside the range that transport systems can handle. Lipids follow the same pattern. Without adequate emulsification, large fat aggregates limit enzyme contact and reduce the generation of absorbable components. Transport systems enforce these structural requirements. The intestinal membrane accepts only defined molecular forms, and anything outside that range is excluded. Larger peptide fragments, partially reduced carbohydrates, and poorly organized lipid components do not cross into body. They continue through the intestine, contributing to downstream processes such as fermentation rather than absorption. The presence of these nutrients within the lumen does not translate into availability within the system. Timing and flow further influence extraction. When gastric emptying and intestinal motility are aligned, substrates are delivered in a steady pattern that allows enzymes and transporters to operate continuously. When delivery is irregular, substrates arrive in pulses that exceed local capacity. Enzymes cannot process the incoming load quickly enough, and transport systems cannot absorb it at the required rate. The excess remains in the lumen, reducing the proportion of nutrients that are captured. The physical environment within the intestine also affects extraction efficiency. Uniform dispersion of substrates supports consistent enzymatic activity and absorption. When dispersion is incomplete, regions of high substrate concentration form, limiting enzyme access and creating uneven processing. These localized conditions reduce overall efficiency because portions of the substrate are not exposed to the conditions required for breakdown and uptake. Incomplete nutrient extraction, therefore, reflects a failure of the digestive sequence to convert intake into usable output. It is not a matter of how much food is consumed, but how much of that food is structurally prepared, processed, and transported into the body. When the sequence is aligned, extraction approaches the system's capacity. When it is not, a portion of the available nutrients remains outside the system, reducing the effective yield from the same intake. Mitochondrial energy instability. Mitochondrial energy production depends on a continuous and properly structured supply of substrates delivered from digestion. When proteins, carbohydrates, and fats are reduced, absorbed, and transported in sequence, mitochondria receive a steady inflow of amino acids, glucose-derived intermediates, and fatty acids that can be oxidized in a coordinated manner. This continuity allows energy production to remain stable because substrate availability matches enzymatic capacity within the cell. When digestion is incomplete or irregular, that supply becomes inconsistent, and mitochondrial output reflects this variability. The first disruption appears as fluctuation in substrate delivery. Incomplete digestion reduces the total amount of usable substrate entering circulation, while irregular gastric emptying and absorption create uneven timing. Mitochondria rely on a constant inflow of substrates to maintain stable energy production. When delivery occurs in pulses or in reduced amounts, cells must shift between available fuels, altering metabolic pathways to compensate for changing conditions. These shifts maintain function but reduce efficiency and introduce variability in energy output. Lipid-derived substrates are central to maintaining stability because they provide a sustained source of energy when properly digested and transported. When fat digestion is aligned, fatty acids are delivered over an extended period through structured transport systems, supporting continuous mitochondrial activity. When lipid processing is impaired, this sustained supply is reduced, and the system becomes more dependent on rapidly fluctuating carbohydrate-derived substrates. This increases variability in energy production because these substrates are delivered more quickly and cleared more rapidly. Hormonal signaling amplifies these effects by responding to changes in substrate availability. When nutrient delivery is stable, hormonal signals direct substrates into mitochondria in a coordinated manner. When delivery fluctuates, signaling becomes reactive, shifting between storage and utilization states. This alters how substrates are directed within the cell, affecting the balance between different energy pathways and contributing to instability in mitochondrial output. The internal cellular environment also reflects these changes. Mitochondria operate within a network of enzymatic reactions that depend on the availability of substrates and cofactors. When substrate supply is inconsistent, these reactions cannot proceed at a steady rate. Intermediates accumulate or become depleted, altering the efficiency of energy production. The system adapts by adjusting pathway activity, but these adjustments introduce further variability. Mitochondrial energy instability, therefore, arises from disruptions in the delivery of substrates from digestion through absorption and transport into the cell. It reflects a mismatch between the supply of usable nutrients and the requirements of cellular energy systems. When digestion and transport are aligned, substrate delivery supports consistent mitochondrial function. When they are not, fluctuations in availability force the system into continuous adjustment, reducing stability in energy production.